Our video today is going to cover slope of linear equations, or the slope of a line. So we have here three ways that we can think on the slope of the line if we look at it in more direct mathematical terms. The rise over the run, the change in y over the change in x, also referred to as delta y over delta x. The little triangle means delta in there is the Greek letter for that. Or y2 minus y1 over x2 minus x1. Now, if we're taking a step back from the kind of true mathematical way of thinking on the slope is basically the steepness of a line. How much is it increasing as I go left to right? How much is it decreasing as I go left to right? Is it really steep? Is it very gradual? Any kind of information like that. So the slope is generally written out as a single number, a positive, a negative, a fraction, a decimal, or we could even have a slope of 0 showing up. And there's nothing wrong with that. It just represents a unique sort of slope that we'll see in a couple examples later on. Now, to go through and actually find the slope and calculate that, we absolutely need 2 points to be able to find that. There's a few ways that we can find this, and we're going to go through a couple ways that it can show up in problems, but the main two are finding those 2 points either graphically or algebraically to find and calculate the slope. Then when we look at graphs and we're told find the slope of this line using this graph, we want to find or plot 2 points on a set of axes. Sometimes we're going to be given a graph in its entirety or with a whole bunch of points that are on there. It is at that point in time your choice which 2 points you would like to use on that graph. I'm taking this process from the example of if you're given points and you need to solve for it graphically, this is what we need to do. Very similar if you were given a graph, you would just pick 2 points on there all the same. Now the second step, this is going to seem a little bit weird until we actually go into and look at 1 or 2 examples with this. But we're going to create a triangle between those 2 points and determine the rise and the run from one point to the other. Essentially, how much am I moving up or down from the first point to the second point, and how much am I moving left or right from the first point to the second point. Those correspond with the rise and the run, respectively. It should be noted that when we are using this method, the sign and the direction absolutely does matter in this step. That will determine and tell us later on if we're going to have a positive or a negative slope for this overall line. So we will and do need to track that as we are going through and doing this second step. After we have the rise over the run, or it's sometimes also referred to as the change in y and the change in x, respectively, as we see them here and our general parts up here, we're going to plug those values in for the rise and the run, or the change in y over the change in x. That's going to result in some kind of a fraction showing up there. And we are then, at the very end, going to simplify this thing down. This is a great example of why we want to simplify fractions, because it's much easier to look at a slope of 1 over 2, or 1/2, rather than a slope of 50 over 100, and think on what that looks like. It's a bit easier to have a tangible idea of what a reduced fraction and slope looks like, even though they are the exact same thing. So this is our process that we will use if we're going through and finding these things graphically. And then we also have our algebraic method that we're going to be using and seeing as well. So this is one that we would use if we are just given 2 points, like we have with our examples down here, and we're told find and calculate the slope between these 2 points, like what we see here. What we're going to be doing, very similar to our graphic one, we're going to be identifying and labeling the 2 points. So generally speaking, they're given to us. Sometimes we might be given a table of points. At that point in time, you can pick any 2 points on that table that you would like to use. They can be right next to each other, they can be far apart from each other, they can both be have both a positive numbers for x and y, both negative for x and y. Really doesn't matter. We just need 2 points to work with these things. Now, if we're doing this algebraically, my recommendation is that you label one of the points x sub 1, y sub 1, and the other point to be x sub 2, y sub 2. When you're doing this labeling, it does not matter which one is point 1 and which one is point 2. The process that we use to get and calculate the slope overall will take that into account and basically make it so it's not something we need to worry about. So pick one of them to be labeled as one of these, pick the other one to be the other thing, and you can run with it from there. So after we have that decided, we're going to plug x sub 1, y sub 1, x sub 2, y sub 2 into our corresponding equation right down here. Same thing that we had at the top, into this y2 minus y1 over x2 minus x1. This is a way for us to mathematically determine the rise over run, or the change in y's, or the change in x's. We then go through and simplify accordingly from there to get to a single fraction answer or single number answer at that point in time. Now it should be noted, when you are substituting numbers in for y2, y1, x2, and x1, you absolutely must put the number and the sign for each of these things into this equation inside of parentheses. Very often do I see people see, okay, well, y sub 1 is, let's say it's the number negative 3. Okay, well this is y2 minus y1. Well, y1 is negative 3. That's already a negative, so I'll just put in minus and then just put a 3 here and call it good. When actually it turns out if we do that, we would have sign changes that would show up, and that's going to affect our overall problem. So make sure that when you are substituting values in, the number and the sign get substituted into parentheses. If we're missing that, that's generally where errors occur as we go through these types of problems. Now, we have 4 examples that we're going to take a look at. I want to go through both of them in the graphical standpoint, how we see them graphically and calculate the slope through there, and also want to see a couple examples where we go through and solve them algebraically. So I'm going to mix and match these 2 processes with these 4 examples just to give you a good idea of what these things look like and types of ways we can solve them from there. Looking at our first example, we have the points 2, 3 and 4, 6. So we have our graph of those here and graph of the equation. We have our general forms of the slope written out up here as well. We're going to go through and solve this thing graphically first, and then we'll go through using our equation and these 2 points and plugging them in, just to show that there are 2 ways to go about doing this. Now, when we're doing this graphically, we have 2 points that are listed here. We need to figure out which point are we starting at, which point are we ending at. It does not matter which one you choose as the starting point and ending point. You just need to make that decision at the beginning and then commit to that. So I'm going to choose this value here as my starting point, and this point here is my ending point. So now, as per our process and our steps with that, we were told to create a triangle between them and determine the rise and the run. So what this means is, we're going to use red here to illustrate this. If I'm starting at my lower point, I need to determine if I want to do the rise first or the run first. Doesn't matter. I'm going to do the rise because it comes on top and then rise in the bottom here. So from this point, I'm going to notice I'm going to go up here and I'm going to go over. Let me make this nice little triangle showing up right in here. And what's nice about this is a great visual representation of the rise and the run of this thing. A really nice part from here is now I just count up. How many spaces up did I go? Well, I went up 1, 2, 3. So this thing is we call it a positive 3. And then I'm going to the right in the positive direction by 1, 2. Okay, so it's a positive 2. Some people like to put arrows on these just to show the direction we're traveling in. That can be helpful. You're welcome to do that. So I went up 3, then over 2. Great. I now have my rise over my run. So I can write this out off to the side here. Rise over run. And I can just plug in the numbers that I was given, or I calculated, I should say, 3 over 2. So therefore I have a slope between these 2 points and this graph of 3 over 2. Now this is going through and solving it using a graph here. I want to go through and also show how we can do this algebraically. So as per our process, we have our 2 points. We need to label one of these things as x1, y1, and the other point as x2, y2. Does not matter which one is which. We just pick one, label it, and then commit to it. So I am going to choose this first one here to be x1, y1, second one to be x2, y2. I'm doing that pretty arbitrarily. There's nothing special about these points or doing it in this order, so you can reverse it if you'd like. Now off to the side, I'm going to go ahead and divide this up a little bit, give myself some space. I'm going to write out my general equation. So I have that there. Now I'm plugging in x1 and y1 accordingly, and then x2 and y2 accordingly in here as well. And now that I have these accurately plugged in, now I can go through and simplify this whole thing down. And I find in doing so that I am also getting a positive slope of positive 3 over 2. We have our 2 different ways of finding the slope between these 2 points for this first example. Taking a look at our second example, we're going to go through and do the same things that we did previously. So we're going to solve this thing graphically first, and then we'll go through and solve it algebraically second. So with our previous problem, we chose the leftmost value as our starting point, and then the rightmost one as our ending point. I'm going to reverse that for this problem, just to show you that you can do that, and which one you pick really doesn't matter as your starting and your ending point. Very much like which of these is labeled as x1, y1, and x2, y2 doesn't really matter. So in this case, I'm going to start at my point up here, and I'm going to end at my point down here. And like we did previously, I'm going to determine the rise and the run. So I am moving down here. I'm going to put a little label in this little arrow pointing down. I'm moving down by 1, 2, 3, 4, 5, it looks like. So I'm moving down 5. And now moving from this corner over, let's go ahead and put little tick marks in there just so we can see that. Okay, we have our little triangle that's formed here now, and I'm moving over, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I moved 5 in the negative direction vertically. How about horizontally? Well, I'm moving 10 in which direction? The positive direction or the negative direction? I'm moving in the negative direction, so this is going to have negative 10 down here. Okay, can write out, maybe not rise over run, instead maybe you want to use delta y over delta x. That's perfectly acceptable, it means the same thing. So we'll use that instead. What did I find as my change in y values? I found that I went down or decreased by 5. So I can write that in here. And then how much did my x values change? Well, I moved in the negative direction by 10 again. So I get a slope of negative 5 over negative 10. I can simplify this further, and that will become a slope of m equals 1/2. So great. It ends up being the case that this is a positive slope, even though I went in the quote-unquote negative direction with both of these. But again, if we went reverse, if I went up by 5 and then 10 in the positive direction this way, we'd still get to a slope of 1/2. So again, really doesn't matter which way you organize these things, your starting point, ending point. Just pick a starting one, pick an ending one, and go from there. Now let's go through and solve this thing algebraically. And again, with the algebraic process, it doesn't matter which one you label as point 1 and point 2. I'm going to choose point 1 to be this and point 2 to be this. And like we did previously, we're going to write out our general formula for ourselves. I think this is really good to write it out each time to make sure and help us get this solidified in our head. But now I'm just going to plug in my points into here and simplify this thing down. And as we're seeing here, we are also getting a slope of 1/2, just like we did graphically. Should be noted that if you were attempting this on your own, make sure that you did plug in the numbers and their signs inside of parentheses into this formula. We do have sign changes that are showing up here, and if you did not have that when you were going through this, that is generally the culprit for a lot of these problems. Actually, there was an error that showed up. This should be a +4 here. I got ahead of myself. There we go. Change there. It should be a +4, and then the result is 10. Okay. Hopefully we can see where the sign change can show up and can occur, and make sure we're on the lookout for that as we're going through and solving these things algebraically. Our third example is when we start to get into the two weird cases that can and do pretty regularly show up with slopes of lines. So we've been given the points 7, 2 and -2, 2. We'll look at this thing and we're noticing that this is creating a horizontal line. We're still going to use the same idea of solving this thing graphically, but there's a little bit less work that's going to need to be done with this. So we're still choosing our starting and our ending point. We'll say let's start in this left point and we'll end at the right point. So first we need to determine how much am I rising up or decreasing down by. So if we're looking at this, well, this thing isn't going up at all. So if I'm thinking on my change in y or my change in x, or again, rise or run, whichever one you would like to think of, I'm not moving up or down at all. So what's my change in y going to be? 0. It's not changing in any way, shape, and form. The y value is staying the exact same from one point to the other, and we can see that written out in the 2 points here. What about the x values? This is one that we could actually calculate. So I'm going to count over from here. I'm going over 1, 2, 3, 4, 5, 6, 7, 8, 9. So my change in x is going to be a +9. You might think, okay, great, I've got 0 over 9. How do I reduce that down and simplify it? Well, what is 0? Nothing divided into 9 pieces. It's still going to be 0. So my slope for a horizontal line is going to be 0, now and forever. So whenever I have 0 divided by a number, I'm just going to keep getting 0 as my answer. So whenever we see this kind of a graph showing up, a horizontal graph, whether it's up here, here, right on the x-axis, way down here, anywhere in that horizontal line has a slope of 0. Let's go through and I'll write this thing out and solve it algebraically as well. I'll label these 2 points, plug it into this equation, and solve it right here. We can see here, following this same process that we've done with our previous examples, we are getting a slope of 0 for both of them. You might be thinking, well, hold on, I got a -9 down below here. Wouldn't that change something a little bit? And generally speaking, it would change something. But 0, which is effectively nothing, isn't going to change sign from a positive nothing to a negative nothing or a negative nothing to a positive nothing. It just is nothing, and it remains this 0 in here. So we had a slight difference showing up in that regard, but beyond that, we still end up getting to a slope of 0 for this and all horizontal lines. Our fourth and final example has us working with the points 3, 6 and 3, 1. Notice also that we have a vertical line showing up when we graph these things and take a look at what this thing looks like visually. So again, we're going to start with writing out our slope. We're going to use rise over run. Oops. M equals, not miles equals. We got rise over run. There we go. We do need to choose which is our starting point and which is our ending point between these two things. I'm going to start at my higher points and I'm going to end at my lower point here. Okay, so if I'm writing this out for myself, what's my rise going to be? If I'm starting here and ending here, I am moving in the negative direction because I'm moving down. So I'm going to be going down by 1, 2, 3, 4, 5. So my rise is going to be -5 here. Now what's my run going to be? Am I moving left or right or horizontally at all with this thing? No, I'm not. So what's my run going to be represented as mathematically? Well, the run is going to be 0. And here we have an interesting thing that shows up. We have a number being divided by 0. This is the interesting part, and this is where the weird stuff comes in. What is our slope going to be for this vertical line? Well, it can't be 0 because 0, as we saw with our previous example, means that it doesn't rise up or down at all, and this thing clearly does. It can't be 1 because it doesn't have a positive increase vertically and positive increase horizontally at all. So this thing, because of the division by 0 that is showing up in here, this thing is going to have an undefined slope. We would write that in just as undefined. Depending on the class or the program that you are using, this might be written out, or they might give you a drop down or some different options with this. But for the purposes of my class, if you're taking mine and doing tests with me, I will be looking for your slope to be written out as undefined for this problem. We do not know what the slope is. We do not know what exactly or how exactly we can order it and phrase it. The reason it is undefined is depending on the way that you want to look at this, which is our starting, which is our ending point, the slope could either be theoretically infinitely negative, like it's just going down infinitely from one point to another point, or in contrast to that, it's increasing infinitely. If I'm starting here and moving up, then it's going up by an infinite number of numbers with each point that we have. So positive infinity or negative infinity as the slope. Which one would it be? We don't know. We still don't know. So this is yet another reason why we list this thing as undefined as the slope for vertical lines. And again, we're going to go into and go through this algebraically, but anytime you have a vertical line showing up, it is always and forever going to have an undefined slope, whether we do that graphically or what I'm going to do here shortly is solve this thing algebraically. If you still get a number divided by 0, it is undefined. So we'll go through and write out solving this thing algebraically right over here, and then we'll wrap things up from there. And we're seeing that we are, even going through it algebraically, getting an undefined slope showing up. So, any time that you see a vertical line or you have division by 0 for a slope, your slope is going to be labeled as undefined for your final answer. As a recap of the material that we covered today, we were working with the slope of a line. We had our 3 different definitions or mathematical definitions of the slope. We can and we will be working with all of them. So I would recommend writing those down and having those somewhat close and nearby as you're going through and working through these problems. Regardless of the form that we are working with, or whether we are calculating the slope graphically or algebraically, we need at least 2 points to be able to go through and calculate the slope of a line. And with that, we had our method to solve these things graphically, we had our method to go through these things algebraically, and our 4 examples that went along with that. Remember that our 2 examples at the very end, a horizontal line always has a slope of 0. And our very last one, a vertical line, is always going to have an undefined slope. This is for these 2 examples or any other instance that these 2 things show up in any kind of graph or problem that you are working with. Horizontal lines are always going to have a slope of 0. Vertical lines are always going to have a slope that's undefined. So we have a couple extra or last things here for you. If you want some practice, I'd recommend pausing the video here and writing these down and trying to calculate the slope for yourself between each of these points in our different problems here. I think it's worthwhile to go through and try it graphically also, but at the very least I'd try it algebraically. We'll scroll down, and here are our answers to each of these. Hopefully these went well for you. If you did notice that you got the answers slightly or somewhat off, make sure you go back and double check that everything is being labeled properly. X sub 1, Y sub 1, X sub 2, Y sub 2, and also being plugged into that general equation properly inside of parentheses, especially when there's negative signs, because that can throw all of this off. But otherwise, that is everything for our 4.4 material, the slope of linear equations.